Dear students, my name is Ivana Šestak, working as Associate Professor on Faculty of Agriculture, University of Zagreb from Croatia, and within the model Smart Agriculture, my next lecture is Chemometry in Spectral Data Analysis. I already talked in a few former lectures about spectral properties of soil and vegetation which are used for agricultural purposes and about soil spectroscopy and proximal sensing. Spectral data can be also obtained from the drones or from the satellite images. They are independent data used for building prediction models. As example, we use soil spectral analysis to estimate soil properties by calibrating conventional reference measurements like soil wet chemistry, which we do in a laboratory, to the spectral signatures we get from the sensor. Calibration samples must be representative. Sampling plan is the first step, a very important step during the procedure flowchart to use soil reflectance data for building prediction models of specific soil properties of our interest. On the picture below on this flowchart, we can see that we start from soil sampling. We need to have a good soil sampling plan to cover spatial variability of specific soil property. We can do in situ proximal sensing and take spectral reflectance on the moisture samples in the field, or we will prepare it for lab analysis. We need to reduce the moisture effect if we do analysis in the field. Data analysis starts with data preprocessing and preparation for building calibration model. Simultaneously, we also do wet chemistry, standard analytical methods to obtain reference values for specific soil properties. Accordingly, when we have reference values obtained by wet chemistry and our pretreated and preprocessed spectral data, we apply chemometrics. These are specific statistical or mathematical models to find relation between reflectance of electromagnetic radiation from soil samples to the values obtained with wet chemistry. We build prediction model and validate it with independent samples to get the accuracy and precision of the model and to see if we can use it again for unknown samples with similar agroecological conditions. Frank and Kowalski gave a well-known definition of chemometry. Chemometry can be defined as a chemical discipline that uses chemical, statistical, and other methods based on logical explanations for our purpose to ensure maximum chemical information by analyzing chemical data. So it complies calibration, multivariate statistics to build prediction models. In spectroscopy and remote sensing, we model interaction of solar energy with biophysical material, soil, plant, water, or rocks. If the connection between the reflected energy and biophysical character of the material is successfully determined, then the inversion of the model can measure the reflected energy and actually give us a result. It can predict the state, concentration, or content of the biophysical material depending what we are measuring, vegetation or soil. On the example of the soil as a matrix, due to overlap of the absorption spectrum of different soil components, the spectral response is very indeterminate with many overlaps and multicollinearity. So it is necessary to extract the information by different mathematical methods and then to find some variability in it and variations which can be connected to the variations in the soil properties. So the soil spectral analysis requires the use of multivariate calibrations. What we will do through the practicals is to do some spectral transformation, preprocessing and pretreatments. Original spectral data are pretreated and transformed by different algorithms to mitigate and prevent the influence of noise in the data during the measurement process and to reduce this collinearity which we have in spectral data and overlapping of absorption peaks, for example, water, minerals, organic matter, especially in the near infrared. I will shortly explain each of these preprocessing methods we usually use. Here is the first derivation mathematics which we use to reduce multicollinearity. First derivation shows the level of change in the reflectance absorption of radiation at each wavelength, and it is more pronounced when you use first derivation. Second derivation corrects the influence of ambient noise during measurement and difference among overlapping reflectance peaks. Mathematical derivatives are useful for reducing the influence of radiation scattering due to the geometry of sample, surface roughness of the sample, and to find these clear position features. Smoothing aims at reducing high-frequency noise, like some spikes in the spectrum, and try to smooth it. For that, we use moving average window approach and Savitsky-Golay algorithm. Moving average window analyzes data points by creating a series of averages of different subsets of the full data set to reduce these spikes. And Savitsky-Golay algorithm is based on a moving window that fit polynomial curve of a fixed degree to the spectral data. It is assumed that the fitted values are better estimates than the measured ones, and therefore that some noise is being removed in the process. Savitsky-Golay smoothing together is very easy to apply and can be used to calculate smoothed first and second derivatives of the signal together. Multiple scatter correction is a mathematical procedure for the correction of scattering within the spectrum caused by different physical conditions during the measurements: particle size, solid structure, light scattering effects, atmospheric conditions, if that is the case of remote sensing. MSC minimizes these deviations by fitting a linear model between a reference spectrum, which is then average of all spectrum dataset, and other spectrum dataset using a linear least square method. Then we use standard normal variates, which indicate how much the measured values are higher or lower than the average of its standard deviation units. It performs normalization of the spectra, which is calculated by subtracting each spectrum by its own mean and then dividing it by its own standard deviation. It is also very useful to correct spectra for changes in optical path length, surface roughness of sample, and light scattering. Visible and near-infrared calibration is the equation that expresses the relationship between electro-optical parameters and the compound of interest. Most common calibration methods used are linear methods like multiple linear regression, principal component regression, and partial least square regression. There are non-linear methods like artificial neural networks. Through the visible and near-infrared calibration, we can define specific wavelengths important for finding these relationships. Equation is usually a linear sum of products. Principal component analysis in a near calibration process is very important because we want to reduce the dimensionality of the data. Variability described by spectral data can be calculated through extracting new latent variables or principal components that are linear combinations of data from all wavelengths and explain most variations. Multiple linear regression is often used as a linear method for modeling large data sets in cases where we have already defined principal components from the spectrum and there are few and they do not correlate between themselves, and we can see that this relationship is really linear. PLSR analyzes numerous and collinear independent variables. It is a full spectrum method and it seems reliable to derive relevant information from very large data matrices. It combines PCA and MLR prediction. Regarding the non-linear methods, we apply machine learning. Artificial neural networks are applied when the complexity of the problem overcomes our human neural network and when it is non-linear. It tries to simulate neural connections in our brain with these massively interconnected nodes to find these relations. It summarizes representative data and then runs algorithms to automatically learn the data structure. That's the ability of ANN to associate complex spectral information with the characteristics of the measured property without restrictions in the distribution of samples or something. And because of that, it makes it ideal for describing some complex nonlinear relationships that exist, especially in the agroecosystems and in nature, where we have a lot of numerous factors which can actually make the situation nonlinear. During the calibrations, outliers can be marked and removed from further analysis as a result of different conditions regarding measurements, physical condition of the sample or instrument noise. How can we analyze performance of the prediction model? We use statistical parameters like bias, that is a mean estimate of the difference between predicting and reference value, mean error, standard deviation, which is a measure of scattering the dataset, then standard estimation error, or standard calibration error, which estimate the calibration accuracy for unknown sample, standard error of prediction, which is the accuracy of that prediction, root mean square error as well as a measure of accuracy, coefficient of determination as explained variance by the model. Very good parameter for measuring accuracy and precision of our prediction is RPD, ratio of performance to deviation. which is calculated as a standard deviation of the reference sample done by wet chemistry and by root mean square error of the prediction. There are many advantages of proximal spectroscopy in the visible and near-infrared part of the spectra. Several parameters can be analyzed simultaneously just from one reflectance curve. It is non-destructive, non-invasive, there is a minimum sample preparation, and a lot of parameters can be measured in a very rapid way in one analysis. The results of spectroscopy analysis are very strongly correlated with the result of the standard laboratory analysis. It enables more intensive sampling because it is non-destructive and then accordingly reduces the cost of laboratory analysis. It identifies the specific wavelengths used to detect certain objects and materials before obtaining remote sensing data, so we can use it as a reference for remote sensing. Some disadvantages is that calibration is still empirical and it is still under the research. We need reference sample data to build calibration model because we cannot use calibration model which is done on one specific soil type on some other soil type because it is totally different material, different medium and agroecological conditions. There is some inaccuracy and uncertainty which occur in different steps within the assessment process. First in soil sampling, then during the measurements, during the development of calibration model and choosing calibration model and final spatial predictions. There is a certain loss of precision and accuracy, but for purposes of precision farming, soil survey and agri-environmental monitoring, it is really enough precise. Today, Global Soil Laboratory Network, founded by FAO, try to enhance and support the development of all types of soil spectroscopy at national, regional and global levels. There is a need for these calibration scales and levels and improvement of internal quality standards, standard protocols and controlled conditions. If we improve that, we can compare data from different spatial levels and geographic levels with greater accuracy. Glossolan also support countries in establishing their own soil spectral laboratories and national soil spectral libraries with standardized methods and decentralized estimation services. The objective is to build the spectral databases to improve the assessment of quantitative or qualitative soil properties to get the information in the more rapid and enough precise way. Thank you for your attention.